What if the deadliest American weapon of the war was not a bomber, not a battleship, not even the atomic bomb, but a tiny device buried deep inside an artillery shell, quietly listening for its target? How did a radar brain small enough to travel inside a spinning projectile become the invisible hand behind burning aircraft, shattered attack waves, and broken offensives from the Pacific to the Ardennes? It was not size. It was not armor. It was a weapon designed for one purpose only: to decide the perfect moment to kill. The radar proximity fuse could detonate so precisely that entire crews never even saw what hit them. To understand how this device became the most effective secret weapon of the war, we must go back to a time before shells could think. Long before anyone imagined a shell that could think. The battlefields of the late 1930s and early 1940s were shaped by a brutal truth. Artillery and anti-aircraft guns, despite their size, noise, and power, were astonishingly bad at hitting anything that moved. During the Great War, gunners had averaged more than 8,000 shells for every aircraft destroyed. By the beginning of the next war, as aircraft grew faster, climbed higher, and maneuvered more violently, the ratio had swung even further against the defenders. It didn't matter if the men firing the guns were veteran crews with steady hands or newly trained units bracing for their first air raid. The shells they sent skyward had almost no chance of meeting their target. The first winter of the conflict made this failure painfully visible. In the skies above London, barrage balloons drifted like steel-tethered whales. Anti-aircraft guns thundered night after night. And yet the bombers kept coming. When the all-clear finally sounded each morning, the streets were littered with shattered glass. The smell of dust and burning timber hung in the air, and Londoners stepped out of crowded underground stations to discover entire blocks erased. Citizens whispered a grim joke: the guns are louder than they are useful, because everyone could hear the batteries firing, but few saw any bombers falling. Lookout crews would scan the sky, prepare the fuses, set the elevation, and fire thousands of rounds upward. Most bursts erupted hundreds of feet from their intended targets. A few came close. Almost none mattered. The shells detonated too early, or too late, or too far away to send fragments into the thin, vital organs of a moving aircraft. It was like firing heavy stones at birds flying through wind and darkness. A gun position might expend all its ammunition in a single night without scoring a single kill. On the ground, the problems were different, but the results were no better. Infantry trusted entrenchments because history told them to. A deep foxhole or a reinforced dugout had protected soldiers for centuries. When a high-explosive shell detonated on impact, most of the force and fragments radiated outward, lethal to anyone caught in the open, but survivable for soldiers below the surface. A well-dug position often meant the difference between life and death, especially in the frozen soils of northern France or the thick forests of Eastern Europe. Entire doctrines of defense were built around the idea that overhead cover and deep earth always provided sanctuary. The war's early campaigns reinforced this belief. In Poland, France, North Africa, and Norway, artillery duels followed the same old patterns: explode on contact, take shelter, wait for the barrage to lift, then counterattack. Even when new guns emerged, longer barrels, faster rates of fire, a timed fuse could be set to detonate after a calculated flight time. But in real combat, amid smoke and panic and inaccurate range estimates, these fuses rarely achieved their intended effect. A mistimed shell might burst harmlessly overhead or explode prematurely, wasting its force before reaching enemy lines. Meanwhile, aircraft grew into the greatest threat of the modern battlefield. Dive bombers plunged downward with terrifying precision, their sirens howling, dropping explosive charges directly onto tanks, trenches, and moving convoys. Torpedo bombers skimmed across wavetops, releasing weapons that could cripple or sink warships with a single strike. High-level bombers rained destruction over cities, factories, ammunition dumps, and ports. Anti-aircraft crews stood at their stations, tracking the incoming shapes, adjusting their sights, and firing until their shoulders ached, but always too late, too inaccurate, too slow. By 1941, commanders in every theatre recognized a grim equation. The firepower of their guns no longer matched the speed and agility of their enemies. A destroyer escorting a convoy might fire several hundred shells at a single attacker without doing more than scratching the paint on its fuselage. A coastal battery guarding an important harbour might expend its ammunition supply before bringing down even one aircraft. And on land, soldiers huddled beneath tree roots or piled sandbags, hoping the next bombardment struck just a little farther away. The problem wasn't courage. Crews manned their stations under fire, reloaded under falling debris, and aimed through smoke and concussion blasts. The problem wasn't steel or explosives. Both were abundant. The problem was timing. Artillery needed a way to detonate its shell at precisely the right moment, neither too far nor too close, but within a narrow sphere of lethal efficiency. The most powerful guns in the world became nothing more than noisy machines producing impressive but ineffective displays of fire. Naval commanders felt this frustration acutely in the Pacific. Japanese dive bombers, flying in tight formations, could descend upon a carrier group with terrifying speed. Yet even a wall of fire couldn't guarantee a single hit. Pilots learned to weave, climb, dive, and exploit the delay between visual contact and explosive burst. A shell detonating just 15 feet too far to the side was as harmless as one exploding half a mile away. The consequences were deadly. Carriers burned. Destroyers capsized. Cruisers limped back to port trailing smoke. Survivors recalled watching their own shells burst beautifully, symmetrically, and uselessly, while the attacking aircraft flew straight through the pattern unharmed. Something was deeply wrong with the very foundation of modern firepower. Even radar, which revolutionized detection and interception, couldn't solve the timing issue. Radar could track an incoming aircraft, calculate its approximate altitude and speed, and relay that information to gunners. But once the shell left the barrel, the rest depended on physics, prediction, and luck. Air density, wind, the plane's evasive movements, and even minor calculation errors all conspired to render most shells ineffective. It was becoming clear that the war was shifting towards speeds, altitudes, and attack angles that conventional artillery simply couldn't handle. If the Allies couldn't find a new way to destroy fast-moving aircraft, the cost in ships, cities, and lives would continue to rise. And so, before anyone dared whisper the words, proximity fuse, the war stood on the edge of a technological cliff. The old tools were failing. The enemy adapted faster than expected. Entire defensive systems, anti-aircraft batteries, coastal guns, field artillery were showing their age. Aircraft roamed too freely. Bombers struck too precisely. And the ground, once the ultimate refuge, could no longer guarantee safety. By 1942, this imbalance threatened to tilt the war in the Axis favor. Luftwaffe bombs continued to fall on Britain. Japanese aircraft mauled Allied ships across the Pacific. German artillery devastated American positions in Tunisia and Italian mountains. A single well-aimed barrage could pin down entire battalions, stall offensives, or shatter counterattacks. The Allies needed a way to make artillery intelligent, to let the shell itself determine the moment of detonation, regardless of human calculation, weather conditions, or evasive maneuvers. The solution had to be small, rugged, shock-resistant. It had to operate flawlessly inside a spinning projectile heated by friction and buffeted by air currents. But the looming catastrophe of the air war and the escalating brutality on the ground forced the Allies to search for something unprecedented. A device that didn't just explode on impact, or after a timer, but by sensing the presence of its target. A fuse that knew where its enemy was. A fuse that could think. A fuse that would, in time, become the most effective secret weapon the Allies deployed. The search for a weapon that could change the mathematics of the war began long before the first American laboratory was mobilized. In late 1939, as Britain braced for the air assault that everyone feared but no one could yet describe, to a young scientist named William Allen Stewart Butemont, quietly submitted a proposal that would redefine the battlefield. Butemont, working alongside Edward Shire and Amherst Thompson at the British Air Defence Establishment, recognised that traditional timed fuses were no longer sufficient. Aircraft moved too quickly, their speeds unpredictable, their approach angles too varied for any human calculation to reliably anticipate the perfect detonation moment. Butemont's idea was radical, a fuse capable of sensing its target rather than waiting for a timer or physical contact. He envisioned a miniature radio detection system, essentially a tiny radar transmitter and receiver nested inside an artillery shell. When the shell approached an aircraft, its own radio waves would bounce off the target, altering the signal in a way that could trigger detonation at maximum lethality. The concept seemed almost miraculous, yet it was grounded in physics and the emerging science of high-frequency radio. No existing electronic components could survive the forces generated during artillery firing. When a shell left the barrel of a gun, the internal acceleration exceeded 20,000 times the force of gravity. Vacuum tubes, the fragile glass hearts of all 1930s electronics, shattered instantly under such load. Even if they survived the initial shock, the intense spin of rifling, often reaching 30,000 revolutions per minute, would tear internal filaments apart. Radio circuits were delicate instruments, not hardened machinery. A fuse of this type needed to endure punishment that no radio device had ever survived. Yet Britain had little choice but to attempt the impossible. In 1940, German aircraft swept across Europe with grim efficiency. London endured night after night of bombardment. Anti-aircraft crews did everything possible, but the limitations of their fuses made accurate defence nearly unattainable. In desperation, the air defence establishment pursued Butemont's concept, constructing early prototypes and testing them in unrotated projectiles, small rocket-like launchers that produced far less stress than artillery guns. These tests proved the concept's scientific validity, but also exposed the technological chasm that lay ahead. The circuits functioned only under gentle acceleration. None survived conditions resembling real combat. British scientists recognised that the project demanded industrial capabilities and large-scale experimentation far beyond what a nation under continuous aerial bombardment could sustain. In September 1940, a delegation led by Sir Henry Tizard crossed the Atlantic with a locked black metal box containing Britain's most closely guarded technical secrets. Within it lay magnetron designs, radar advances, jet engine research, and the embryonic proximity fuse. Their destination was Washington, where the United States, still officially neutral, possessed the one resource Britain could no longer command: an untouched industrial base and the ability to conduct research without fear of bombing. The American scientific community, under the direction of Vannevar Bush at the National Defense Research Committee, understood immediately the significance of what the Tizard mission carried. Among the American physicists summoned to examine the documents was Merle Anthony Tuve of the Carnegie Institution's Department of Terrestrial Magnetism. Tuve, already a respected researcher for his work in nuclear physics and ionospheric studies, had the rare blend of theoretical precision and hands-on engineering ingenuity required to tackle a problem of this magnitude. Bush placed him in charge of Section T, the new group assigned to develop the fuse from concept to battlefield weapon. The meeting between John Cockcroft, the British physicist presenting the fuse concept, and Tuve became one of the most decisive scientific exchanges of the war. Cockcroft explained the British research, the prototype successes, and the insurmountable limitations imposed by the physics of artillery firing. Tuve left the room with an understanding that the task before him was unprecedented: to create electronics that behaved like radio instruments but survived like hardened steel. By December 1940, the Carnegie Institution laboratories in Washington, D.C., had transformed into the heart of the American effort. Tuve assembled a team of scientists whose names would later anchor entire chapters of American scientific history. Richard Roberts brought expertise in nuclear reactions. Henry Porter contributed knowledge of acoustics and wave behavior. Robert Broad specialized in cosmic ray physics. Lawrence Hafstad offered deep understanding of nuclear instrumentation. Lloyd Berkner, already famous for his research on the ionosphere, joined to tackle signal detection challenges. Among them was a young physicist named James Van Allen, who would eventually discover the Earth's radiation belts, but began his scientific career trying to keep radio tubes alive inside exploding shells. The team confronted physics at its harshest. Traditional vacuum tubes were fragile glass bulbs, their internal filaments suspended on fine wires. Under the crushing shock of artillery launch, these components collapsed instantly. Van Allen turned to industries skilled in miniaturization, specifically hearing aid manufacturers like Raytheon, seeking designs that eliminated fragile suspensions and replaced them with robust mechanical supports. Months of trial and failure followed, but by early 1942, Van Allen introduced a solution: a shock-resistant tube structure with internal components held rigidly in place, reducing the chances of catastrophic deformation during firing. It was a mechanical triumph disguised inside a few centimeters of glass. Meanwhile, Berkner advanced the crucial radio detection principle. Instead of relying on a single oscillator to transmit and detect signals as the British concept proposed, he refined a circuit that improved detection, reliability, and minimized sensitivity to noise and vibration. This innovation brought the device closer to functioning as a true proximity sensor rather than a crude timing device. The project soon outgrew its initial laboratory space. In spring 1942, Johns Hopkins University established the Applied Physics Laboratory, APL, specifically to expand and coordinate the proximity fuse program. The building repurposed for this mission had been an automobile dealership, still bearing the smell of oil and rubber when the first researchers entered. Within weeks, it became one of the most advanced electronics research centers in the world. Under Tuve's direction, the culture inside APL was driven by urgency. Every delay meant casualties. Every improvement meant lives saved. One of the most daunting challenges emerged from the battery. A shell fuse component could not rely on traditional power sources, which degraded over time and failed catastrophically under acceleration. The National Carbon Company developed a radical solution: a reserve battery that remained inert until the moment a shell was fired. The acceleration shattered a glass ampule of electrolyte, and centrifugal force pushed the liquid across metal plates to activate the battery during flight. This process ensured the fuse delivered full power only after leaving the barrel, solving the long-standing problem of shelf life and reliability. Safety mechanisms demanded equal innovation. A fuse too sensitive risked detonating near friendly forces or inside the gun barrel itself. Engineers incorporated multiple safeguards: centrifugal switches that remained open until the shell spun at combat velocity, timer circuits that introduced deliberate arming delays, and sensitivity curves calibrated to reach their peak only at operational altitudes. The fuse needed to wake up gradually, stabilizing itself in flight as it scanned for its target. To the scientists involved, the complexity of the device became almost mythic. Inside a casing barely 2 inches in diameter, they were packing a transmitter, receiver, amplifier, battery, triggering tube, safety circuits, and detonator, all hardened to withstand enormous forces. It was the equivalent of building a radio station inside a projectile hurled from a cannon. Every week, test failures reminded the team how unforgiving the problem remained. Circuits tore loose, tubes fractured, batteries activated too early or too late. Radar interference drowned out the return signals. Tuve and his colleagues repeatedly returned to their designs, recalibrating and refining each component. They confronted a reality few engineers had faced before. The device had to survive conditions more extreme than almost any machine ever built, yet behave with the sensitivity of a scientific instrument. Still, progress accelerated. By the middle of 1942, test firings from naval 5-inch guns began producing stable, functioning fuses. Engineers documented successful detonations near drone targets, an achievement once believed impossible. The war would soon test it in the skies over the Pacific, the fields of Europe, and the cities threatened by flying bombs. But before it reached the battlefield, the scientists had to conquer secrecy, manufacturing, logistics, and the last doubts of commanders who had never seen a shell capable of thinking. By the time the Proximity Fuse project moved into full-scale development, the war had entered a phase in which every month carried measurable consequences in lives lost. The scientists working under Merle Tuve understood this with a clarity that bordered on obsession. The Applied Physics Laboratory, once a dusty car dealership displaying Buicks and Chevrolets, became a fortress of secrecy and urgency. Instead of customers browsing vehicles, military guards patrolled the entrances, checking identification, while inside, physicists worked under blackout curtains, surrounded by workbenches overflowing with soldering irons, oscilloscopes, metal casings, and fragile experimental tubes. Every hallway smelled of warm bakelite, hot solder, and machine oil. Engineers bent over prototypes, adjusting microscopic components beneath magnifying lamps. Technicians in white coats carried trays of vacuum tubes the size of a thumb joint, each one hand-assembled and tested. Even the simplest conversation was restricted by classification. Workers used nicknames for circuits, disguised terminology for tests, and avoided saying radar anywhere outside secured areas. The Proximity Fuse carried a level of secrecy rivaling the Manhattan Project, and its laboratories reflected the weight of that responsibility. Early prototypes demonstrated promising behavior, but still failed frequently during tests. A typical morning might begin with optimism as the team mounted a new design into a firing shell. Then came the controlled test run. The firing table shuddered, the shell blasted forward, and engineers waited for the telltale signal on their monitoring oscilloscope. Too often, the trace remained flat, silent evidence of another shattered circuit or dead battery. Tuve insisted on direct data, not assumptions. He often stayed late into the night, studying test fragments brought back from firing ranges, sorting through tiny shards of copper, glass, and steel. Each shard revealed clues about what had failed. A bent wire might indicate rotational stress. A scorched filament suggested premature arming. A cracked battery plate pointed to insufficient shock absorption. Nothing was discarded until every lesson was extracted. The team soon recognized that solving one problem often created another. When Van Allen improved the internal rigidity of the vacuum tube structure, the increased stiffness led to new vibration modes during flight. When Hafstad adjusted the amplifier stage to increase sensitivity, the circuit picked up too much noise from the shell's own spinning motion. When Roberts modified internal supports to protect delicate connectors, the added mass shifted the fuse's center of gravity and disrupted ballistic performance. Each breakthrough demanded another adjustment. Yet these failures were part of a pattern. Every problem solved brought them closer to the one device that could survive the launch of a naval gun. To accelerate progress, Tuve insisted on parallel development tracks. One team focused on battery activation, another on frequency stability, another on safety switches, and another on antenna design. Communication between teams, while constrained by secrecy, allowed ideas to cross-pollinate. A technique borrowed from hearing aid miniaturization contributed to tube design. Knowledge from cosmic ray counters influenced shielding. Principles from acoustics helped stabilize oscillators. The fuse became an interdisciplinary machine long before the term became common. Early trials had used low-stress firing platforms, but by late 1941, the team transitioned to full naval guns. At the Dahlgren Proving Ground in Virginia, long racks of 5-inch Mark 12 guns awaited the next experimental batch. The first time a proximity fuse survived firing from a full-power naval weapon, the engineers monitoring the range felt a collective shift. The oscilloscope trace gathered microsecond echoes from the drone target. A moment later, the detonation signature appeared not delayed, not premature, but precisely where it needed to be. Still, one success meant nothing without reliability. A combat weapon needed to work under every condition. Heat, cold, humidity, vibration, altitude change, and rough handling. Thus began the most punishing test regimen of any wartime electronic device. Fuses were placed inside temperature chambers, cycling from Arctic cold to Saharan heat. Others shook violently on mechanical tables, simulating the turbulence of flight. Some endured drop tests, spin tests, acceleration tests, and dozens of repetitive firings. Failure rates declined slowly but steadily. Each improvement marked the shrinking of the gap between laboratory success and wartime readiness. As reliability increased, industrial challenges emerged. A single proximity fuse required more than 100 precision components. No factory in America had ever built such devices in the required quantities. The military and the Office of Scientific Research and Development reached out to companies with specialized skills. Western Electric for miniature components, Raytheon for tubes, Sylvania for mass vacuum tube production, Crosley for assembly. These factories needed to be taught not just what to build, but how to build it. Blueprints arrived with missing labels on purpose, so that workers handling components would never know the final purpose of what they assembled. Training new workers became its own campaign. Women arriving at Crosley's Cincinnati assembly lines learned to solder tiny resistors and capacitors under strict supervision. They worked in long rows, hands steady, eyes straining beneath magnifiers. Each component required precision. A wire 1 millimeter too long could throw off the circuit's resonant frequency. A solder joint too thick could break under acceleration. Workers were told only that they were contributing to a war-essential electronics program. Almost none knew they were building a weapon that would soon knock enemy aircraft from the sky with machine-like efficiency. As winter 1942 turned into 1943, the fuse approached operational reliability. Yet secrecy remained the one uncompromising requirement. The Germans and Japanese had strong scientific establishments of their own. If either Axis power gained access to even a damaged fuse, they might reverse engineer its principles or develop countermeasures. The military imposed a strict rule. Proximity fuses could not be used anywhere they might fall into enemy hands on land. Their first battlefield would not be Europe, but the vast open ocean where unexploded ammunition sank beneath deep water. Meanwhile, scientists at APL continued refining every parameter. One group perfected the conical antenna at the fuse's nose, discovering that just a slight change in taper could dramatically alter signal stability. Another optimized the oscillator tube, ensuring it emitted steady radio energy even after the violent shock of firing. Porter's research stabilized the beat frequency detector, enabling it to distinguish between genuine target reflections and noise caused by air turbulence. Berkner's improvements in filtering circuits minimized false triggering. By the time the fuse design entered large-scale production, the project had already reshaped American wartime science. The laboratory structure, government-funded, academically supervised, industrially supported, created a model that would dominate military research for decades. The proximity fuse was not merely a weapon, but a demonstration of what coordinated scientific mobilization could achieve. With production accelerating, the Navy selected its first test platform. The USS Cleveland conducted early combat trials, firing at radio-controlled drone aircraft over Chesapeake Bay. Observers from the Bureau of Ordnance watched as shell after shell burst near the target, shredding drones with uncanny regularity. What was supposed to be a multi-day test barely lasted hours. The results were so decisive that the Navy ordered immediate deployment for Pacific operations. The proximity fuse had crossed the threshold from laboratory marvel to battlefield weapon. Final assembly lines ramped into continuous operation. Trains and trucks carried sealed crates to naval armories. Ammunition handlers quietly inserted green-banded shells into magazines under strict instructions to treat them as classified. Gunnery officers received confidential briefings explaining the fuse's capabilities and limitations. Crews were told only that they were handling special ammunition. Tuve monitored the transition with mixed emotions. The fuse that had consumed years of relentless effort was finally leaving the laboratory. It was about to confront real enemies, real aircraft, real stakes. For the scientists, the next phase combat would become the only evaluation that mattered. The stage was set. The first proximity fuse would soon detonate in combat, and the war would never look the same again. By early 1943, pallets of green-banded proximity-fused shells sat quietly in naval magazines across the Pacific. Their outward appearance differed only slightly from standard ammunition. Yet, inside each casing, a miniature radar system waited to prove itself. For months, officers and scientists had debated the moment of first combat use. The risk of premature deployment was severe. If a shell failed to detonate or fell into enemy hands intact, the Axis powers might dissect the fuse's secrets. But the growing intensity of Japanese air attacks left little room for caution. The fuse had been built for a single purpose, defending the fleet, and its time had come. The cruiser, USS Helena, became the first ship chosen for operational use in January 1943. While steaming near Guadalcanal, Helena's radar operators detected inbound aircraft. They were Aichi D-3, Eval dive bombers, veterans of earlier Pacific victories, now approaching to attack American positions. The ship's gunnery crew moved with practiced precision, loading fresh rounds and scanning the sky for visual contact. Beneath their feet, sealed in metal magazines, the proximity fuses represented the culmination of thousands of laboratory hours, countless failures, and innovations that had only recently seemed impossible. The first salvos left Helena's 5-inch guns in bright arcs, streaking toward the formation. For years, naval operators had grown accustomed to the disappointing sight of shells bursting too far from targets to inflict real damage. This time, something changed. As one shell passed near the lead bomber, it detonated mid-air with a symmetrical blast, releasing a sphere of fragments that tore into the aircraft structure. What should have been a near miss, instead, became a catastrophic kill. The bomber's wing separated, its engine caught fire, and the aircraft spiraled downward before crashing into the sea. Observers on Helena understood instantly that a threshold had been crossed. A shell had not merely exploded, it had chosen the perfect moment to do so. Moments later, additional bursts illuminated the sky. Japanese pilots attempted evasive maneuvers, banking hard to escape the incoming fire, but the shells compensated for their movement. They did not need direct hits. They only needed proximity. Within seconds, another attacker disintegrated in the air. A pattern formed. Burst. Debris. Splash. Years of defensive frustration evaporated in a single engagement. Scientific theory had become devastating reality. The impact of this success rippled through the Pacific Fleet with remarkable speed. Navy commanders soon learned that even small numbers of proximity-fused rounds dramatically increased a ship's defensive capability. Carriers, cruisers, and destroyers that once relied heavily on fighter cover now possessed the ability to repel air attacks with unprecedented efficiency. Reports from ships equipped with the new shells documented kill ratios that exceeded anything previously achieved by conventional ammunition. In many cases, the number of rounds required to destroy an aircraft dropped to a fraction of earlier figures. While the Pacific bore witness to the fuse's naval triumphs, a different threat loomed over Europe. In the summer of 1944, Germany launched the V-1 flying bomb offensive against London. The pulse jet-powered missiles followed a persistent trajectory, difficult for conventional gunners to intercept. British and American anti-aircraft crews initially struggled, achieving modest success rates even with radar-guided fire. The arrival of proximity fuses transformed this defensive campaign almost overnight. For the first time, the guns could detonate shells near the fast-moving missiles without requiring direct hits or perfect timing. During the second and third weeks of the V-1 offensive, success rates increased dramatically. By the fourth week, the defensive batteries destroyed nearly 4 out of every 5 incoming missiles. London, which had braced for catastrophic losses, instead witnessed a rapid decline in impacts. The combination of SCAR 584 radar, M9 gun directors, and proximity fuses created a defensive barrier that kept thousands of civilians alive. Each intercepted missile represented a family spared a neighborhood preserved, a hospital or rail yard that remained operational. The fuse's effect extended far beyond tactical benefit. It became a shield over the heart of a nation. Yet the most shocking demonstration of the fuse's power emerged not over oceans or cities, but in the dense forests and snow-covered fields of the Ardennes. In December 1944, during the opening days of the Battle of the Bulge, German infantry advanced through thick winter fog, supported by armor and artillery fire. American forward observers, tracking these movements, soon recognized that the German assault threatened to overwhelm defensive positions scattered across narrow forest corridors. At the headquarters of the 406th Artillery Group, Colonel Oscar Alfred Axelson faced a critical decision. His ammunition bunkers contained thousands of proximity-fused shells recently delivered with strict orders restricting their use on land. The risk of capture remained too great, but the German offensive was rapidly gaining momentum. American units on the front lines faced overwhelming pressure, and conventional artillery fire struggled to slow the advance. Axelson weighed the risks. The consequences of inaction could be catastrophic. He issued the order. Proximity fuses would be used immediately, aimed to burst above advancing enemy formations. When the first salvos detonated, the forest canopy flickered with flashes of white and orange. Unlike traditional impact shells, which exploded after hitting the ground or trees, these shells burst dozens of feet above German soldiers. Fragmentation cascaded downward in a cone pattern, penetrating foxholes, bypassing overhead cover, and reaching soldiers who believed they had taken adequate shelter. German units accustomed to surviving artillery bombardments found themselves exposed from above for the first time. Survivors described trees shredding into splinters, snow turning black with debris, and entire squads collapsing within seconds. Infantry who had endured years of combat on the Eastern Front and in Normandy now faced a threat that ignored terrain, trenches, and defensive preparations. The belief that a dug-in position offered relative safety disappeared in an instant. Men fled back toward the tree lines, only to encounter more airbursts among the branches. The Ardennes, long known for its thick forests and natural cover, became a lethal trap when illuminated by proximity fuse explosions. Field reports from American observers documented casualty estimates that exceeded anything previously achieved by standard artillery barrages. Artillery commanders requested additional proximity-fused rounds repeatedly, recognizing that this single technological shift had altered the course of the battle. At higher headquarters, senior officers assessed the change with increasing urgency. What began as a desperate countermeasure evolved into a defining element of the Allied defense. Within days, General Dwight D. Eisenhower authorized unrestricted use of the fuse across the European front. American artillery units rapidly integrated the new ammunition into their firing plans. Soldiers who had heard rumors about a smart shell now witnessed its effects firsthand. Infantry, who once feared the vulnerability of exposed ground positions, gained renewed confidence as artillery support became more effective than ever before. Across two theaters, Pacific waters, and European forests, the proximity fuse demonstrated the same principle. Dominance through perfect timing. It did not replace artillery. It redefined it. Instead of relying on carefully calculated trajectories, it delegated the final decision to the shell itself. In doing so, it elevated every gun crew, strengthened every defensive line, and protected every formation that operated under its reach. The Axis powers struggled to understand what was happening. Japanese pilots reported aircraft disintegrating in mid-air with no visible hits. German infantry described shells that appeared to sense their presence. Intelligence units sought fragments to analyze, but few intact samples existed. When German engineers finally examined a captured fuse in late 1944, they misinterpreted its internal construction. Their conclusion was that no vacuum tube could survive the acceleration forces of artillery firing. They had the device in their hands and still could not accept that the Americans had achieved what their own research had deemed impossible. The proximity fuse had crossed from prototype to weapon with astonishing speed. Its battlefield introduction marked a turning point, not only in tactics, but in the psychology of warfare. and the world would never return to the era before this moment. Long before the proximity fuse reached mass deployment, American and British planners understood that its value did not lie only in its destructive capability. Its true power came from something less visible: the inability of the Axis powers to detect, decode, copy, or counter it. The fuse's effectiveness depended as much on what the enemy didn't know as on what Allied gunners could now achieve. As the war expanded across continents and oceans, the device moved quietly through supply chains, onto factory lines, and into ammunition lockers, shielded behind a wall of secrecy that became one of the war's most successful security operations. The term variable time fuse, chosen by Navy officer Captain Sherman Shoemaker, concealed the device's true purpose. The official documents referred only to VT ammunition, a description intentionally vague and misleading. Within laboratories and ordnance bureaus, the simpler phrase proximity fuse circulated among cleared personnel. But for the thousands of sailors and soldiers who handled the ammunition, the shells were simply marked with colored bands and stored under strict instructions. Crews received no explanation of the circuitry inside. They needed only to load, fire, and record the results. The secrecy was so absolute that even many senior officers remained unaware of the weapon's internal function until years after the war. Factories that produced the fuse components maintained similar restrictions. At Sylvania Electric, Crosley Corporation, and Western Electric, workers assembled miniature radio tubes, resistors, antennas, and internal frames without ever learning the purpose behind them. Security personnel inspected employees entering and leaving the buildings, searching bags and coats to ensure no parts left the premises. Supervisors instructed workers not to ask questions and not to speculate. They were told their parts contributed to an aircraft radio program. Nothing more. For many, the truth did not emerge until long after victory in Europe Day. This secrecy proved essential. Throughout the war, German and Japanese scientists explored proximity detonation technologies of their own. Yet none approached operational success. The reasons were numerous: industrial fragmentation, shortages of critical materials, insufficient testing capacity, and widespread damage to research facilities caused by Allied bombing. But the most decisive factor was that the Axis powers underestimated the feasibility of constructing ruggedized vacuum tubes capable of surviving extreme shock. By the late 1930s, Germany had excelled in physics, chemistry, and engineering. Laboratories at Hamburg, Berlin, and Munich conducted early research into acoustic, photoelectric, and electrostatic proximity concepts. Yet each approach encountered limitations. Acoustic fuses triggered prematurely from environmental noise. Photoelectric systems required stable light conditions. Electrostatic detectors failed under fluctuating humidity. When German engineers briefly experimented with radio-based systems, they rejected the concept almost immediately. Their calculations suggested that no miniature electronic tube could withstand the forces of artillery firing. The reasoning was scientifically sound, until American scientists proved otherwise. Captured German documents later revealed frustrated remarks from researchers who examined proximity fuse fragments recovered in late 1944. Engineers from Rheinmetall-Borsig and the Wehrmacht Weapons Office concluded that the Americans must have created some kind of hardened crystal detector or exotic magnetic trigger. They refused to believe the internal tubes were functional after launch. That disbelief prevented Germany from allocating serious resources toward replicating the weapon. Japan faced an even greater barrier. While Japanese physicists possessed strong theoretical understanding of radio principles, their industrial base lacked the capacity for mass-producing miniature tubes with precise internal tolerances. The Navy Technical Research Institute experimented with photoelectric and magnetic fuses, but none survived live testing. As American naval gunners downed more and more aircraft with uncanny accuracy, Japanese pilots attributed the phenomenon to improved gun directors, refined radar fire control, or among some crews a rumored death sphere that expanded outward from American ships. Few suspected the shell itself was making the decision. Meanwhile, American production expanded at a pace no Axis nation could match. Under the direction of the Bureau of Ordnance and the Applied Physics Laboratory, industrial partners scaled operations continuously. By mid-1943, Crosley Corporation's Cincinnati plant assembled thousands of fuses daily. Sylvania's Ipswich Mills facility produced vacuum tubes at unprecedented speed, and Western Electric's standardized quality control procedures that ensured consistent performance across millions of units. All of this occurred while maintaining strict compartmentalization. Workers at one plant never saw the components manufactured in another. Even managers lacked awareness of the complete assembly process. This manufacturing surge enabled the Allies to allocate proximity fuses where they mattered most. In the Pacific, ships defending carrier groups and amphibious landings received large shipments first. The increase in accuracy transformed the nature of naval engagements. Aircraft that previously required heavy fighter screen protection now faced defensive fire far more lethal than any combination of gunnery methods used earlier in the war. Japanese attack formations, once capable of inflicting severe losses in coordinated strikes, witnessed their numbers shredded before reaching release distance. As the weapon entered wider service, the Axis powers noted distinct patterns. Japanese submarine commanders reported that American escort ships maintained a defensive envelope far more effective than anticipated. German reconnaissance flights near the Bay of Biscay, once used to track Allied convoys, suffered increased attrition. Luftwaffe aircraft approaching British ports found themselves targeted with unusual precision, especially near Antwerp and London. Yet despite field reports, intelligence agencies failed to identify a central cause. The fuse's invisibility ensured that its impact appeared as a statistical anomaly rather than a technological revolution. The secrecy extended beyond battlefields. When the first intact proximity fuses were recovered by German forces during the Ardennes offensive, their analysis led to a misinterpretation that ultimately benefited the Allies. Engineers concluded the fuses must have been defective or decoys intended to mislead. The internal vacuum tubes, still intact due to robust casing, were dismissed as non-functional artifacts. With Germany's resources stretched thin, no effort was made to replicate them. Even the Soviet Union learned of the fuse through espionage rather than battlefield capture. Julius Rosenberg, working at Emerson Radio, provided Soviet intelligence with fuse components and descriptions of their assembly process. Soviet scientists reproduced the technology during the late stages of the war and early Cold War, eventually deploying proximity-fused shells during engagements in Korea. Yet even this transfer did not diminish the fuse's wartime advantage. By the time the USSR integrated the technology, the conflict in Europe had already ended. On the Allied side, secrecy remained rigidly enforced. American batteries, using proximity fuses in the Ardennes, were ordered to burn any unexploded shells on the field. Naval gunners received instructions to log all spent ammunition and to retrieve fragments whenever possible. Range debris was buried, smashed, or transported back to secure testing sites. Even sailors who observed the fuse's effectiveness received no technical explanation. They simply saw aircraft break apart and fall from the sky with unnerving reliability. The device's invisibility created strategic effects far beyond the number of enemy units destroyed. Once frontline commanders recognized its reliability, they incorporated proximity fuses into firing doctrines. Artillery officers coordinating counterattacks relied on rapid bursts of air-detonated fire to halt advancing formations. Naval task forces maneuvered more confidently, knowing their anti-aircraft belts could repel mass raids. Anti-aircraft units defending ports and cities achieved kill ratios never imagined at the start of the war. No new evasive maneuver, no revised trench tactic, no defensive adaptation negated the fuse's advantage. The battlefield changed in the fundamental sense that innovation had outpaced countermeasures. By 1945, the proximity fuse was no longer merely a weapon, it was a strategic imbalance. It multiplied the power of every gun that fired it. It defended cities, convoys, airfields, islands, and infantry lines with equal efficiency. And because it remained almost completely misunderstood by the Axis, It operated without meaningful resistance. The secret weapon had earned its title not through silence alone, but through the enemy's inability to see a solution because they never fully grasped the problem. By the dawn of 1945, the proximity fuse had become more than an innovative device. It was a quiet axis upon which the final year of the war turned. From the dimly lit gun bays of destroyers in the Philippine Sea to the frozen artillery dugouts along the Elsenborn Ridge, the fuse reshaped tactics, expectations, and the very logic of battlefield survival. Soldiers, sailors, and officers who had once accepted the limitations of artillery found themselves wielding a weapon that behaved unlike anything in military history, a weapon that operated with its own sense of timing, free from human error and mechanical guesswork. Its impact emerged not merely from lethality, but from the collapse of long-established doctrines. Infantry units that had trained for years in entrenchment tactics discovered that traditional shelter offered diminishing protection. A dugout no longer guaranteed safety. A foxhole no longer shielded a squad. Airburst patterns triggered by proximity fuses reached downward into positions once considered secure, altering the balance between offence and defence. To reports from the Ardennes, and later from the Rhine crossings, described German formations attempting older defensive manoeuvres, only to be caught beneath expanding clouds of fragmentation that descended with unparalleled precision. Commanders adjusted quickly. American ground forces refined dispersal methods to minimize losses from counterfire. Engineers emphasized overhead cover in fieldworks. Forward observers integrated proximity fuses into time-on-target missions, producing devastating synchronized airbursts over advancing enemy formations. The tactical value of a well-coordinated barrage increased dramatically, giving Allied artillery the kind of reach and reliability previously reserved for elite air units. At sea, the transformation was even more profound. Naval gunnery officers recognized that proximity fuses extended the defensive perimeter of every task force. Instead of relying solely on combat air patrols or the intricate ballet of fighters intercepting enemy bombers, the fleet now possessed its own lethal envelope, a constantly shifting sphere of radar-triggered fragmentation waiting to ignite. Aircraft attempting torpedo or dive bomber attacks faced bursts that aligned not with the fall of a shell, but with their own closing distance to it. Those who survived early salvos entered patterns of deadly airbursts, shredded before reaching attack range. During the battles around the Marianas, Leyte Gulf, and later Okinawa, the proximity fuse delivered measurable strategic consequences. The attrition rate inflicted on Japanese air units escalated so sharply that entire waves dissolved before coordinating attacks. Carriers that once braced for impact now held their formations with newfound confidence. Destroyers, cruisers, and escort vessels, often the most vulnerable ships in earlier phases of the war, gained protective layers that altered fleet tactics. The proximity fuse reduced dependence on massive fighter screens and allowed naval task forces to maneuver more aggressively across the Pacific. Its defensive value extended to cities far from open ocean. London's survival against the V-1 flying bomb offensive owed as much to proximity fuses as to radar and fighter aircraft. Anti-aircraft batteries equipped with the new fuses formed a defensive belt that grew increasingly effective over the summer of 1944. The steady improvement in intercept rates, from barely a quarter of von-second downed in the first week to nearly 80% within a month, demonstrated how quickly the fuse scaled when combined with advanced tracking and computing. Each successful engagement prevented a missile from striking civilian neighborhoods, rail hubs, power stations, and hospitals. The proximity fuse did not simply destroy weapons. It preserved the infrastructure of daily life in a besieged capital. On the continent, cities such as Antwerp depended on the same defensive system to remain operational. The port, vital for supplying Allied armies pushing into Germany, became one of the most heavily targeted locations of the war. Thousands of von-second launched from the Netherlands streaked toward the harbour, and only the fusion of CR-584 radar, accurate gunnery, and proximity fuses prevented catastrophic losses. The success rate, achieved by anti-aircraft units, defending Antwerp exceeding 90% during peak activity, stood as evidence of the fuse's strategic value. Without this defensive umbrella, the port could not have sustained the logistical demands of Allied operations. Perhaps the most overlooked contribution of the proximity fuse was its psychological influence. Soldiers and sailors, who once regarded artillery as a blunt tool, began to describe it with reverence. They witnessed shells detonating at the exact moment of maximum effect, repelling attacks that once seemed unstoppable. Conversely, enemy units confronted a battlefield where familiar rules no longer applied. German infantry, accustomed to surviving bombardments by hugging trench floors, now faced weapons that neutralized their primary defensive technique. Japanese pilots, trained to evade anti-aircraft fire through tight turns and sudden dives, saw their maneuvers rendered useless. This erosion of confidence weakened offensive strategies across both Axis theatres. As the war neared its end, historians, military analysts, and political leaders evaluated the fuse's cumulative impact. Vannevar Bush described the weapon as one of the three most decisive American scientific contributions of the conflict, alongside radar and the atomic bomb. For Dwight Eisenhower, the fuse's arrival during the Battle of the Bulge marked a critical turning point, preventing German forces from overwhelming already stretched Allied lines. Naval leaders measured the fuse's value not only in aircraft destroyed, but in ships and crews saved, estimating that dozens of vessels would have been sunk without the protective envelope it provided. On factory floors across the United States, the legacy of the proximity fuse took a different form. Tens of thousands of workers, many of them women, had assembled components under strict secrecy. They handled tiny resistors, coils, capacitors, and tubes without ever being told what they were building. Some labored in facilities repurposed from Christmas light factories. Others worked in garages, warehouses, and converted bakeries. Their collective effort demonstrated the scale of American industrial mobilization, a partnership of science, labor, and logistics unmatched by any Axis nation. The proximity fuse became an emblem of what such mobilization could achieve. Its influence extended even further into the post-war world. The miniaturized vacuum tube designs that allowed the fuse to survive artillery launch became foundational knowledge for early transistor engineering. The shock hardening techniques developed by James Van Allen later protected scientific instruments aboard the Explorer 1 satellite, enabling the discovery of Earth's radiation belts. The organizational structure of the Applied Physics Laboratory, with its collaboration between academic researchers, government agencies, and industry, became a model for Cold War research institutions. In a sense, the fuse seeded the architecture of post-war technological innovation. Even the geopolitical landscape bore traces of the device's legacy. Soviet access to proximity fuse information, smuggled by espionage within the United States, allowed rapid development of similar weapons, illustrating how strategic advantage could evaporate once industrial secrets spread. The dawn of the Cold War accelerated a new era of technological competition, centered on guidance systems, radar miniaturization, and electronic warfare. Much of that race began with the realization that a shell could contain a machine capable of sensing and responding to its environment. By the time Axis forces capitulated in 1945, the proximity fuse had proven its worth thousands of times over. It had destroyed enemy aircraft, halted armored advances, protected ships, and defended cities. It had preserved supply lines, essential for the advance into Germany, and maintained the integrity of island campaigns across the Pacific. Its integration into artillery doctrines rebalanced entire engagements and saved countless Allied lives. But its most lasting contribution was conceptual. The fuse demonstrated that intelligence embedded within a weapon itself could alter the battlefield more profoundly than raw explosive power. For centuries, militaries had sought greater range, larger calibers, and heavier shells. The proximity fuse marked the beginning of a different path. Precision through sensing. The idea that a weapon could perceive its target and make a microsecond decision initiated the modern era of guided munitions. From radar-guided missiles to GPS-directed bombs, the lineage is unmistakable. As post-war analysts reflected on the conflict's turning points, Many concluded that technological superiority, rather than numerical strength alone, had become the decisive factor in modern warfare. The proximity fuse stood at the center of that conclusion. It compressed scientific theory, industrial ability, and battlefield necessity into a device smaller than a coffee cup, one that multiplied force wherever it was used. In the final months of the war, as artillery crews loaded shells marked with green bands and naval gunners tracked aircraft with steadier confidence, the machine quietly fulfilled its purpose. Its creators Tuve, Van, Allen, Berkner, Porter, Roberts, and the thousands who contributed had delivered a weapon that changed the balance of the war. The proximity fuse did not roar like a bomber or cast shadows like a battleship. It did its work in silence, awakening only briefly in the last instant before detonation. In that instant, it reshaped history.